Welcome back. In this video we're going to talk about vector operations in R3, which is a generalization of the work we did in lesson 1 talking about vector operations in R2. We begin with a discussion of points in R3, which are defined very similar to points in R2. They're defined as ordered triplets of real numbers in the form we give the point a name, and then we have 3 coordinate values for the point. So the point name is written out in front. In this case, we're calling this point P. Just as we did in R2, we use parentheses for the points. If we see a point in R3, the coordinates should be given in parentheses. This is an ordered triplet, meaning we say this is the first coordinate of point P. In the second space delimited by a comma, we call this the second coordinate of point P. And then, of course, in the third space, we call this the third coordinate of point P. Again, we can graph points on the axes by intersecting a first, second, and third coordinate axes at the origin. Let's take a look at an example of 2 points in R3. Let's graph the points O, which we're going to call the origin. This will be 0, 0, 0, meaning I move 0 units along the x-axis, 0 units along the y-axis, and 0 units along the z-axis. And then we'll graph the point P, 5 units along the x-axis, 3 units along the y-axis, and 4 units along the z-axis. We can do so by hand, which is a 3-dimensional graph. In this case, let's let the x-axis come right up towards the camera. I'm going to draw this slightly skewed, so here's the positive x-axis. In this case, I'll draw the positive y-axis at a 90-degree angle. Here's the positive x-axis, positive y-axis. And by using our right-hand rule, my index finger goes up out towards the board. My middle finger is in the positive y. And then the direction of my thumb is the positive z. So I see that z should be coming up out this way, 90 degrees to both of those. And then we can actually introduce tick marks. So maybe say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I should probably label these 1, 2, 3, 4, 5. This is 1, 2, 3, 4, 5. And then the z were 1, 2, 3, 4, 5. All right. The origin, the point O, is at the 0, 0, 0 mark. So I call this O. The point P moves 5 units along the x, 1, 2, 3 units along the y. And I have to be a little careful here. This is where perspective comes into play. So if we look at the same angle, it looks like it's going to be right around there, right, if these two lines are parallel. All right. And then it's going to go 4 units up. So here we're going to go 1, 2, 3, 4. Kind of hard to draw that. And we're immediately seeing why visualization in R3 is best done with software. So this actually should be right under that value there. I need to redraw this. If you are grinning or biting your teeth at home saying, oh my God, it is so painful to watch this guy draw, I agree with you completely. I actually don't like the fact that I'm drawing here. What I want to do is I want to introduce you to that pain so that I can give you the medicine, which is called Mathematica. Okay, kind of see that though? That the point P is 5 units out, 3 units over, and 4 units up. Okay, now that we've drawn this point and we saw that it's really not a good strategy to try to do this by hand, let's boot up Mathematica and see how to do this type of image using that software. All right, let's switch over. Here we're in Mathematica and we have our blank notebook. We'll begin with a quick reminder of the contour plot 3D command. Type in contour plot 3D. In Mathematica, the open and close braces are going to be the input. And I like to comment the end of my code just to make sure that I know what I'm doing here. All right, let's go ahead and graph the XY plane. And we'll do so from, I don't know, -8. So X runs from -8 to 8. Y runs from -8 to 8. And then we also need to determine Z that runs from -8 to 8. Let's go ahead and evaluate this. I could go up here and evaluate cells. And there's my X, Y plane. I'm going to go ahead and change the style of this contour. I want to go directive. Directive allows me to do a bunch of different things. Here I'm going to change it to perhaps blue, and I'm going to put the opacity to 20%. All right. I tend to not like the mesh on contour plots unless I absolutely need it to figure out what the heck it looks like. In this case, I already know what the plane looks like, so I want to have it be see-through. We just stated that we wanted to plot the point 530 and the point 000. In order to do this, we're going to use graphics. This is a primitive that's a little different than the contour plot 3D command. So here, the show command is going to combine 2 different types of graphics together. And we're going to separate them with a comma. So here we have the end show command. And then we should end the comment with the same introduction. So here we're going to go ahead and say graphics 3D. And the type of graphics we're going to use is a point. So the name of this first point we're going to call lowercase o. I reserve lowercases for variables that I define myself. If it's a native Mathematica command, we'll see that the first letter of those commands, the ones that Mathematica provides for us, are with capitals. And thus, I like to use anything that I define with lowercase first to let me know that it's me that's defining it. Okay, so let's go ahead and graph the point 0, and we can see it? Right there, there's the point 0. I would like to actually increase the size of this point. So I'm going to go ahead and turn brackets around here, and I'll say point size. And Mathematica is kind of interesting. Let's go 0.01 to just see how big that is. Okay, let's try 0.04. What is it complaining about? That should be changing the size there. Maybe we'll switch the order. Let's try if that works. Yeah, there it is. Okay, So that's a little too big. It's all up in my face. We could try point 2. Yeah, so that's a little bit bigger. And then maybe we also want to turn this point to red. Okay, so there's the origin. We could also label this thing if we want. Let's plot the point P. And we said that P in our example from our written notes was going to be 5, 3, 4. Right? So let's go ahead and plot the point P. Well, you know what I'm going to do? Oh, that's what it's complaining about. Did you see that there's that comma right there? Mathematica does not like commas at the end of the thing here. And then there should be 2 brackets inside there. There it is. Okay, do you see it? And then the last thing I could do, just to make it clear where these points are, I could put the axes through the origin 0, 0, 0. Okay, see it? So now I have the x, y, z, and I can kind of just by clicking on this thing and rotating it, it gives me those 2 points. And this is a much better way to visualize the value of those points. All right, let's go back to our hand analysis to do an introduction to vectors and vector operations, and we'll come back to Mathematica at the end of this video. Now that we've taken a look at how to graph this, let's introduce vectors in R3. A vector in R3 has both a magnitude and a direction. When we define vectors in R3, we write them as directed line segments, just like we did in R2. Where if we write a vector x, and perhaps x has 3 components. The first component, the second component, and the third component. You can tell that this is a vector and not a coordinate because of the vector hat symbol here. Here's the vector hat written on top. And you could also tell that this was a vector and not a point because of the angle brackets. Here we have the left angle bracket. And here we have the right angle bracket. Just like we did in R2, the individual entries of a vector are called components. This is called the first component of our vector. Here, after the first component, of course, we have the second component. And then finally, right here, we have the third component of our vector. When we look at this vector, we have the same setup as we did previously. Each vector in R3 has an initial point, which will be an ordered triplet, maybe we call it x1, y1, z1, and a terminal point, which will be an ordered triplet, perhaps we call it x2, y2, z2. And the vector itself is a directed line from the initial point, so it's going out of the initial point into the terminal point. If you remember, this we called the tail of the vector because it was away from where the arrow was, and this was called the head. We also call this the initial point, and we call this the terminal point. Just like we did in R2, in this case, if this was the vector x, we would write x as the vector connecting point P1 to P2. And we can see that P1 is the tail and P2 is the head by the direction of this vector hat. So this is the vector connecting those. If we look at the individual components of x, we calculate these as the difference in the coordinates. The amount of the length of the x component is the difference between the x coordinate of point 2 and the x coordinate of point 1. Similarly, the y component or second component is y2 minus y1, and the third component of our vector is z2 minus z1, where each of these is the coordinate of the associated point that defines the vector. Recall, there are infinite number of vectors that have components A, B, and C, unless you are specifically told. So this is a convention that is useful to remember. Unless we are specifically told the initial point of a vector, we can assume the tail is at the origin. In R3, 0, 0, 0. That's just a way to work with this. All right, before we introduce operations on these vectors, let's take a look at how to graph these in Mathematica. Here's the code that we ended with from the previous conversation we had with Mathematica. I have 2 points. I have a contour plot that graphs my XY plane, and then I've combined that with a plot 3D using the show command. The next thing we're going to do is draw another graphics in 3 dimensions. So we'll just copy and paste. But in this case, we're not actually going to use the point because we don't want to draw a point. What we want to do is to draw an arrow, which is known as a vector, that starts at the point 0 and ends at the point P. Let's go ahead and evaluate this using the Shift Enter. It is Mathematica complaining because I have this stupid comma there. When I do the show command, I want each of my internal graphics to be delimited by a comma, but the last one should not have a comma on it because that indicates this. Okay, there it is. Look at that. So now there's my arrow that goes from the 0 position to the P position. And I can actually change the thickness of this arrow. So let's do thickness, perhaps we call it 0.02 just to see what happens. Little thicker, a little bit too thick, isn't it? Thicker than a Snicker here. Let's go one more. Maybe we go a little thicker than that. Yeah, there it is, right? And the really cool thing about this is I can actually change the initial point. Perhaps let's want to call this 1, 1, 1. And should we get a little exotic? Do you want to get a little exotic? Watch this. Let's go -4. Perhaps we go to -2. And let's go to 3. Oh, look at that. Do you see that? So now all of a sudden I can move these points around to get different vectors. This is really powerful. Could you imagine having to draw this by hand? This goes back to the conversation I had earlier. With a little bit of hard work, we become functional in a way that we can achieve output that we couldn't do without this software. In the next video, we'll introduce operations on vectors in R3. See you there.